Okay, so welcome back to this next video in which we are discussing transporters. Okay, right, so in this video what I want to do is contrast channels to transporters. Okay, so we've discussed the motivation for this. We've discussed that hydrophobic molecules can quite easily cross the cell membrane. Okay, but polar molecules cannot. And the reason is that polar molecules will have water molecules associated with them. And I'll just quickly draw you the structure of a water molecule. So basically, if we see our water molecule here, we've got oxygen bound to two hydrogens. Okay, hydrogen nuclei have a much lower electronegativity than oxygen nuclei. So the electrons in this covalent bond are pulled towards the oxygen nucleus and are going to sit closer to the oxygen nucleus. And it's the same for this covalent bond here. So we're going to have a partial negative charge towards the oxygen atom, and then you're going to have partial positive charges towards these hydrogen atoms. Okay, so the oxygen atom will therefore interact with positively charged ions, such as sodium ions, so you'll get water molecules surrounding these positively charged ions. In addition, if you've got a negatively charged ion, what will happen is the the hydrogen atoms this time will face the negatively charged atom. So you'll have a hydration shell all the same, basically. Okay, now, to cross the lipid bilayer, you would have to give up this hydration shell. And in order to do that, you're going to have to put in a lot of energy, basically. Okay, and where do you get that energy from? Well, occasionally, some molecule will just happen to get enough energy to actually do that. So, yes, it will happen occasionally. But it's very unlikely that the solute molecule will actually have the energy to throw away its hydration shell and then move through the lipid bilayer like so. Okay, right. So, what we're now going to discuss is how do we get polar molecules across the lipid bilayer when there are electrochemical potential gradients across the cell membrane in a physiological timescale. Okay, right. So there are two ways: channels and also transporters. And I want to now contrast channels to transporters. Okay, so we'll start off with channels and then we'll move on to transporters. So basically, a channel is an that's fine. A channel is an extremely simple structure, okay, conceptually. It's a membrane spanning protein. Okay, so it's a protein which will sit in the membrane, and basically if we take a cross-section of it, it will look like so. It just has a channel moving through that protein. Okay, so if I draw a more three-dimensional picture, what it will look like is so. Often they're drawn as cylinders, although of course they're not cylinders, they're more complicated shapes, but for simplicity, this is what they generally look like. We've got this nice big cylinder here, and we've got a pore going down the middle. Okay, and the solute molecule, which will generally be an ion of some sort, okay, will move through that pore, and then it can just cross the membrane. And basically, even though often the ions will have to give up their hydration shells when moving through the pore of an ion channel like so, often what will happen is you'll have a number of amino acid residues that line this pore, which will interact nicely with the ion, and basically those bonds will, when they're formed, will release energy, and that will make up for the energy that you had to put in to throw off the water molecules, basically. So you've got a number of polar amino acid residues all the way through the pore, which will interact beautifully with the ion, basically, and make this a much lower activation energy, basically. So the amount of energy an ion needs to move through this pore will be much, much lower, something like that, maybe. Okay, so basically they're lowering the activation energy that an ion will need to actually move across the membrane. Okay, so basically it's just a protein which has this pore running through it, and solute molecules can move through the pore, basically. Okay, let's now contrast this to transporters. because transporters are going to actually change conformation to move the solute molecule, okay? Channels don't change conformation, they are just an open channel basically. They have this pore and the ions can move through, but it doesn't involve any sort of participation on the role of the channel basically. The channel doesn't need to participate in order to actually get the solute through. Okay, let's contrast this now to transporters. Okay, so let me show you a transporter. So basically the idea of transporters is, let's say we're trying to get something into the cell. Basically what will happen is the molecule which needs to be transported will bind to the transporter which is currently in the outward facing state. Okay, so transporters will have two states. They'll have one outward facing state, like so, and then they'll also have an inward facing state. Okay, so let's say we want to move a molecule in. The molecule will bind to the transporter when it is in the outward facing state here. So this is our molecule, our solute molecule that needs to be transported here. And then what will happen is there will be a conformational change. The whole protein will change conformation. And when it changes conformation within the membrane, it will change to what's known as the inward facing state. Okay, like so. And when it's in the inward facing state, it will then release the molecule basically. So this is a key concept, that the molecule, the solute molecule here will have a high affinity for binding to the outward facing state, and then it will have a low affinity for binding to the inward facing state, and will therefore be released once the transporter goes into the inward facing state. And then what will happen is, once the molecule has been released, the transporter will change back to its original conformation, and it can then bind a solute molecule again. So the idea is that when the solute molecule binds to the outward facing state, that triggers a conformational change that turns it into the inward facing state. The molecule then has a low affinity for the inward facing state, cleaves off it, and of course once the molecule is cleaved off, the transporter will change back to the original conformation when it was in the outward facing state, and then another molecule can come and bind. Okay? So the key difference is that transporters have to undergo these huge, great conformational changes to move every single solute molecule that they move across the membrane. Okay, and this means that ion channels can move solute molecules through them extremely rapidly. Okay, so these are fast, whilst transporters are extremely slow basically, because every solute molecule which is transported requires this huge elaborate conformational change on the part of the transporters. Okay, right. So just to emphasize this, these ion channels can conduct up to 10 to the power of 8 ions a second, and the main solute channels move are ions rather than bigger things. Okay, bigger things generally require transporters. So these are extremely fast. They can transport up to 10 to the 8 solute molecules per second. Okay, transporters are nowhere near that fast. You know, we're talking thousands a second maximum for transporters. Okay, right. So now we've seen the basic distinction between channels and transporters. Let's talk about the division of transporters further up into passive transporters and then active transporters. Okay, so channels are absolutely always passive. All they do is allow solute molecules to move, okay? And the direction that you will get a net movement of solute molecules in will be the direction facing the area of the lower electrical potential. So when solute molecules move through channels, they will always move from the area of high electrical potential to the area of low electrical potential. Sorry, not electrical potential, electrochemical potential. They'll always move from the area of high electrochemical potential to the area of low electrochemical potential. Okay. Meanwhile, when we're talking about transporters, some of them will be passive. i.e. they will just move the solute molecule from the area of high electrochemical potential to the area of low electrochemical potential, whilst others can be active. They can actually move them in the opposite direction. Okay, so passive transporters will move solute molecules down their electrochemical potential gradient. Okay, so these are just like channels, but they're much more clunky, basically. So down the electrochemical gradient. Okay, whereas active transporters can actually move things up their electrochemical gradient, so from the area of low electrochemical potential to the area of higher electrochemical potential. Now, to do this, you are going to have to put energy in. Remember, electrochemical potential was all about energy. There was an energy stored in an electrochemical potential gradient. If you are going to move solute against its electrochemical potential gradient, then you are going to make the electrochemical potential gradient worse, basically. You're going to make it even bigger. Okay, so you're going to be making the energy that's stored in that, the ability to do change, bigger. Okay, so you must put some sort of energy into the process to be able to do that. So, where the energy comes from then distinguishes active transporters up into primary active transporters and also secondary active transporters. Okay, so primary active transporters then will move a solute up its electrochemical potential gradient, okay, via coupling the process to some sort of chemical reaction. And the chemical reaction that you usually couple it to is ATP hydrolysis. Okay, so let me draw a little picture for this. So, basically, we need some more paper. So I'll get some more paper. Right, so let's say we have these two compartments then here. Okay, and we're going to move a solute molecule up its electrochemical potential. So let's say the electrochemical potential for this solute molecule is higher in compartment 2 than it is in compartment 1. So the electrochemical potential in compartment 1 is quite low, it's quite high in compartment 2. Okay, and let's say this transporter here is actually going to move the solute molecule up its electrochemical potential, so from the area of low electrochemical potential to the area of high electrochemical potential. Well, basically, you're going to have to put energy in to do this. So you need something that's going to release energy that is then going to drive the movement of this ion up its electrochemical potential gradient. Okay, and that energy is going to come from a chemical reaction if we're talking about primary active transporters, which means that you're going to hydrolyze ATP to ADP or inorganic phosphate generally. This is the main chemical reaction that primary transporters use. Okay, so this is a primary active transporter then in red here. Okay, right. Now let's contrast that to secondary active transporters. So the idea with secondary active transporters is that again, you will move a solute molecule up its electrochemical gradient, but the way that you'll get the energy to do this is by moving another solute molecule at the same time down its electrochemical gradient. So for this example, we need two solute molecules. So let's have solute molecule blue and solute molecule green. Okay, right. So, again, let's have two compartments. So I'll have us here, and here is the membrane here. Okay, like so. And then we've got our secondary active transporter here. Now let's say that the electrochemical gradient for blue is higher in compartment 2. Okay, whilst the electrochemical the electrochemical potential for molecule blue is lower in compartment 1. So these are the blue's electrochemical potentials. Okay, now we'll calculate the electrochemical potentials for green. Okay, and let's say that the electrochemical potential for green in compartment 1 is higher than in compartment 2. Okay, so this now is greater than this. So, basically the idea is that this secondary active transporter can move blue up its electrochemical gradient, okay, from compartment 1 to compartment 2 if it then moves a molecule of green down its electrochemical gradient. So that would be from compartment 1 to compartment 2 because compartment 1 has the higher electrochemical potential for green than compartment 2. Okay, right. And if the amount of electrochemical potential that is released by green moving down its electrochemical potential gradient is equal to the amount that you have to put in to move blue up its electrochemical potential gradient, then that's fine. Usually, the amount of electrochemical potential that you release by allowing green to move down its electrochemical potential will be greater than the amount of electrochemical potential that you need to put in to move blue up its electrochemical potential gradient. Now, if you end up transporting them in the same way, in the same direction like so, then this secondary active transporter will be called a symporter. Okay, so sim means in the same direction, kind of. Okay, so symporter means that they'll be moved in the same direction. If, on the other hand, I had said that the electrochemical potential of compartment 2 for green was greater than the electrochemical potential of compartment 1 for green, okay, so let's say that the electrochemical potential of compartment 1 for green was lower than the electrochemical potential of compartment 2 for green, then green would have obviously wanted to move from compartment 2 to compartment 1, so it would be this direction instead. So you'd need to move green in the opposite direction this time. So now we'd be moving blue from 1 to 2 and green from 2 to 1. In that case, we'd be moving them in the opposite direction, and that would be called an antiporter. Okay, right. So we've seen passive transporters, which are just going to move solute molecules down their electrochemical potential gradient. And we've then seen active transporters, which will move solute molecules up their electrochemical potential gradient, either by coupling it to a chemical reaction, and those are primary active transporters, or by coupling it to the movement of another solute molecule which will move down its electrochemical potential gradient. And providing that the amount of electrochemical potential energy released by the other molecule, which is green in this example, moving down its electrochemical potential gradient is the same or larger than the electrochemical potential energy going into moving blue up its electrochemical potential gradient, then we're fine. Okay, so that now concludes our introduction to transporters.